Perfect. So the next contributed talk is on multi-server Covert learning. And Ruta will give the talk for us, and that's joint work with Justin Holmgren. Thank you so much. Please go ahead.
Okay, actually, okay. Sorry, okay, you can hear me. So I'll be presenting a paper on multi-server covert learning. This is joint work with Justin Holmgren. Oh, yes. Okay. So another perspective which we can take on a model stealing attack is we can consider that a client is attempting to learn a particular target function. And so in this case, like in this kind of setting, we'll consider specifically trying to learn Boolean functions. So now in this, one of the earliest models on learning, like learners, was this work on probabilistic approximately correct learning. And in this model, a client is attempting to learn a target Boolean function, in this case Boolean function, and does so using a table of random examples. And its goal is to learn a function which is close in L1 distance to the target function with high probability. And so a natural model to consider is a setting in which instead of having direct access to random examples, you'll have oracle access to the target function. And so you'll make queries X and receive some replies f of X. And again, in this model, we'll have that the client should learn a good approximation with high probability. And so it's there are works that show that there are classes of functions which are learnable through queries but are not learnable through random examples. And we'll see why this is useful like a few slides. And so now what we will consider is we'll consider a setting in which the client does not have direct access to the target function and instead has there's an intermediary, which is a server. And this server was particularly is restricted to forwarding on queries from the client to the target function and forwarding back the replies from the target function back to the client. And now that we consider this intermediary server, yes, first, of course, we must have that, again, the client should be able to learn something. So our definition of learning is that the client should learn an approximation with good probability. And this is the completeness of our definition. But now that we have this intermediary server, we can actually think about privacy in this setting. So when we think about privacy, we'll have that, so the client's interaction with the server that we're thinking of specifically in this scenario is a semi-honest server that is like observing these queries and attempting to learn more information, such as information that Alice might have or a client might have specifically about the target function. So what we say is that in order to have privacy, there must exist a simulator which behaves as both the client and target function and interacts with this semi-honest server in such a way that this simulator is able to generate a transcript which is indistinguishable from the client and target functionality's transcript with the semi-honest server. And in order to aid the simulator in this task, the simulator is given a set of random examples. And so this is particularly important because, as we mentioned briefly in PAC learning, we see random the client is given random examples, and there's a difference between being given random examples and having direct query access. So if the semi-honest server just sees random examples or something which is indistinguishable from random examples, then the semi-honest server shouldn't be able to learn anything more than what would be PAC learnable. So leveraging like this gap between what is considered to be query learnable and PAC learnable is important in this line of work. So this is the completeness and privacy properties belong to this definition called covert learning, which Ari also mentioned in the previous talk. So now we'll actually switch to a slightly different setting, but quite a natural setting, which is that instead of considering one server, we'll consider that the client is interacting with multiple servers. And in this setting, the client is attempting to learn the function, a good approximation to the function with high probability. And in the privacy setting, we'll specifically consider the setting in which the k-1 out of k servers are semi-honest. And once again, we'll say that there needs to exist this simulator which interacts with the k-1 out of k semi-honest adversaries and is able to generate a transcript which is indistinguishable from the client's transcript. So now that we've discussed this multi-server setting, I'll briefly mention some previous work in this line of covert learning. So there's this cryptographic sensing paper from 2019, which in the multi-server setting shows under no assumptions that a client can learn O log n juntas, and juntas here are functions that depend on a subset of the inputs, so input bits. So in this case, it's O log n out of n input bits. And so they are able to do this and achieve perfect privacy. And a subsequent work is specifically on covert learning by Kennedy and Karchmer, worked in the single server setting and showed under the LPN assumption that you can learn polynomial and n-size decision trees under, because it's based on LPN, they get computational privacy. And in comparison, our work is in the multi-server setting and under no assumptions is able to learn a larger class of functions, which are the Fourier sparse or Fourier concentrated functions. And Fourier sparse functions are linear combinations of parity functions, which we'll talk about in the next slide or the next few slides. And since they are under no assumptions, we'll get that they have perfect privacy. Our main technique is actually based on the original Fourier theoretic version of the Goldreich-Levin algorithm. So this is importantly different than the later popularized version of the Goldreich-Levin algorithm, which is taught in classrooms. So we'll see the Goldreich-Levin algorithm in this form in later slides. So just to give a brief explanation of the difference between Fourier sparse functions and juntas in decision trees, as done in previous work. So cryptographic sensing paper worked on O log n juntas, which are a subset of polynomial n-size decision trees, as in the later work. And the Fourier sparse functions are a superset of both of these classes. And to illustrate the difference, like what types of functions we're able to learn that previous works have not been able to learn, we'll look at an example, which is the class of parities. And so parities in this case are a multiplication of a few, any subset of the inputs, any subset of bits from the inputs. And so as you might guess, it has an overlap with O log n juntas in the particular case when the subset is O log n, it's sized O log n. And so let's consider in the two server setting how we might learn a parity, an arbitrary parity. So The client will send a uniform random string R to the first server, and will then send the same uniform random string with the first bit flipped to the second server. And continuing on, the client will then send R prime to the first server, and then R prime with the second bit flipped to the second server, and continue on, flipping the third bit, flipping the fourth bit, and so on. And here we'll just note that since each server's view is actually that they see completely uniform random queries, and as such is not like in the setting which we have 1 out of 2 semi-honest servers, it will be perfectly private. And so now I'll discuss how does the client actually learn the parity given the answers to these queries. So if the answer to the query R is different from the answer to the query R with the first bit flipped, then the client is able to note that the first bit is important to the parity. So it's included in the subset of bits that are multiplied. And so again, the client can do this for all the remaining bits and learn the entire parity function. Okay, so now I have explained how to learn one parity, but I mentioned that Fourier sparse functions are a linear combination of a few parity functions. And so now we have to extend this idea to the Fourier sparse functions. So in order to do this, I'll first introduce some Fourier analysis definitions. So if we're considering functions that specifically operate from 1, -1 to the n to 1, -1, then we'll define a Fourier basis, which is just exactly these parity functions that we mentioned earlier. And then now we can represent this function in terms of the Fourier basis, and we'll call this Fourier decomposition. And here the constants associated with each parity function, we call them Fourier coefficients, and importantly, they can be calculated in as an expectation of the function value on the input and the specific parity function with the set that you're attempting to compute the coefficient for. So using this information, we'll say that, well, one way that we can actually get an exact that we can exactly compute our function f is that if we were able to exactly compute all the Fourier coefficients. So clearly we must have a good approximation if we can approximate all Fourier coefficients. So if we attempt to do this and find all Fourier coefficients for every single set, and here we'll represent, just to understand, we'll represent the set as a binary string where the 1 indicates whether the element is included in the set or not. So then in this case, we'll notice, well, we have to evaluate it for every single binary string, and this will lead to an exponential runtime. So, well, in order to actually figure out what to do from here, let's actually look back at our Fourier decomposition, and we'll introduce this terminology, which will become clearer to see why later, called a Fourier weight, which is just the Fourier coefficient squared. And so now we can actually look at our Fourier decomposition in terms in which the Fourier weight is heavy. So the Fourier coefficient squared is sufficiently large, and the terms for which the Fourier coefficient squared is smaller. And by dividing it up into these two groups, we can actually do the following, which is that we can get a good approximation if we just drop all of the light Fourier weight terms, since the heavy weighted Fourier terms have a much larger influence on how the function behaves. And so now this is actually the crux of the covert learning algorithm, is that we will find all heavy Fourier weights. So now, in order to find all heavy Fourier weights, we'll end up needing to use a little bit of a little bit of a trick, which is that we'll consider the tree of all set prefixes. So we'll consider all sets that have the prefix 0, all sets that have the prefix 1, 0, 0, 0, 1, and so on. And now what we'll end up doing is that we will prune prefixes that have a light Fourier weight. And what this will do is it'll actually eliminate the entire rest of this tree, starting at this prefix. So we'll eliminate every single set that has the prefix 1. So now, just to reiterate this, I'll explain by another way, which is this is actually the Goldreich-Levin algorithm. And so we start with all sets in one bucket. And what we'll do is we'll split each bucket into 2 different buckets where we'll fix the prefix. So in this case, we'll split the set of all the bucket of all sets into all sets that have the prefix 0 and all sets that have the prefix 1. Then we'll weigh each bucket according to the Fourier weight. And in this case, since we're using the squared term, we're better able to compute the we're better able to get, so since the Fourier weight, Fourier coefficient can be negative, we'll get even the largely negative terms included. And we'll keep only these heavy buckets. And using these heavy buckets, we'll recurse and repeat until we're finally left with a collection of sets for which the Fourier weight is heavy. And so in order to get a sense of how to do this, recall that if we just naively attempt to compute all sets with the weight of all sets with a certain prefix, that will again end up having this exponential runtime problem. So luckily for us, there is a nice efficient way to compute the weight of a bucket using more Fourier analysis, which is that the weight of the bucket can actually be computed as another expectation, which is correlated queries to the function. And so the correlation is specifically that the first part of your query will be uniformly random to both of these queries, and the second part is the same. And so we'll see that in our algorithm itself, we'll just compute an estimation of this. But now that we have this correlated query idea, this is actually sounds pretty similar to the parity example that I gave earlier, in that what the client will do is simply split these 2 correlated queries across the 2 servers. So one server will end up seeing uniform random for the first part, and then the correlated part for the second. But since that correlated part is uniform random in and of itself, each server will end up seeing uniform randomness. So it is again secure or private against 1 out of 2 semi-honest servers. Okay. So yeah, this is almost the conclusion, which is that you can extend this to the multi-server setting if you consider the last part being an XOR, and if the XOR is equal to 0, then that's the correlation that you need to induce for this to proceed to go through from the multi-server setting. And the first part is again uniformly random. And yes, that's the main idea. So thank you, and the paper will be available soon.
Thank you so much, Ruta. Thanks. So unfortunately, I think we have to take the questions offline for the interest of time, but thank you so much. So the next speaker can please come. Hello.